Sir, exam was like very like fine, sir. Like good for me.
It was not very difficult or anything, right?
Yeah, so it is not difficult. It was
Yeah.
not difficult.
What about Rajdeep?
Yes, it is also good for me.
Good. Vaibhavi?
Yes, sir, it was okay.
It was not so difficult, right?
Yeah, yes.
Yeah. So initially, all of you were worried and all that, right? We want mock test and all those things. Any questions this week?
No, sir. I don't have a question for week 5.
Okay. I think after the exam, everybody got tired and they're not joining.
So there was a one question.
Hmm.
Uh, why fall detection in a sequential circuit is complex than a combinational circuit? So I wrote there that in a sequential circuit there is a lot of in sequential circuit the output of current output is depend on the previous output. So is there any if there is any fault in previous output, it also affects the current output. And the sequential circuit is little bit complex than a combinational circuit. So fault detection is very like difficult than a combinational than a combinational circuit. So is it correct or partially correct or incorrect?
Which question is it? I forget.
So
So
there was
explain
a
why
one question.
sequential circuits are harder to test than combination circuits.
Yes, sir.
See, in sequential circuits, controllability and observability are a problem, right? Uh, you can't control the state, correct?
Yes, sir. Yes, sir.
State in which the circuit is something that we can't control, and we can't also observe. Okay, these are not brought out as primary inputs and primary outputs. So that is what I wanted you to write.
Yes, sir. But I studied this thing in week 5 only.
Mm-hmm.
So I wrote there up to my like knowledge from
Oh,
DSD or
acha, acha. Okay, let us see.
Yes, sir, the quiz syllabus was till week 4 only.
Mm-hmm. Okay. What else? Anything that is not clear? No questions?
No, sir. Like from week 5, I don't have any question.
Okay. All right. What about you, Vaibhavi and Rajdeep?
Yes, sir, same with me.
Yes, sir. Same. No doubts in week
So
5.
you have viewed the sequential circuit, that video, sequential circuit testing.
What, sir?
That sequential circuit testing. Have you guys viewed the video yet or not yet?
Sir, like in week 5, there is a like introductory part of sequential circuit testing.
Mm-hmm. So
Yeah.
have you already seen the video or not yet?
Yes, sir. I seen up to week 5.
Mhm. Okay, what is a sequential circuit?
Like, sir, in a sequential circuit, like is a made up of combinational circuit with some extra memory elements like flip flop, latches, and
Mm.
one reset thing and a clock thing like this.
Mhm. Correct. What about Rajdeep?
Yes, sir. Basically, I have not gone through the week 5 properly, completely. But
Mhm.
up to that, I have no doubt.
No, but you may have done, you may be aware of sequential circuits, right? So I'm just curious to know what is a sequential circuit. Vaibhavi?
Yes, sir, like it has clock and all.
Mhm. See, clock is really not a hallmark of a sequential circuit. Okay. See, there are what are called as asynchronous circuits. You may have come across, right? It
Yes,
take a very simple latch. Okay. Have you come across the word latch before?
Yes, sir. In DST, we studied about it, or
Yeah.
like a BDS, basic digital system.
Right. Right. Is this a sequential circuit or a combination circuit?
Sir, it's a combinational circuit.
No, this is actually a
Sir,
sequential circuit.
so
Okay.
that gate is a NAND gate, na, sir?
Yeah, both of them are NAND gates. See,
Okay, so it's a, I guess we are trying to make uh, memory elements from NAND gate. Like in latch or flip flop, in latch we made from NAND gate only. I cannot rem.
right, right. No, don't worry. You may have come across the circuit before. Don't worry about that.
Okay, sir.
Just think and tell me whether it is a combination circuit or a sequential circuit.
Uh, Sir, it's a combinational circuit, like sequential circuit, I guess.
Hmm.
Uh,
Why?
for example, if we are trying to feed input to the second NAND gate,
Hmm.
then the second input of the second NAND gate is the output of the first uh, NAND gate.
Hmm. Okay. See, if I don't tell you what is inside and just treat it as a black box,
Yes, sir.
so see, suppose I put 1 1 on this and I ask you what is the output. Will you be able to tell me what the output is?
Yes, sir. 1 second.
So if I give a 1 1 here, can you tell me what the output is? What, Vaibhavi?
Sir, the output of like one, okay, 1 and 0.
See, let me call this A and B if you want. Okay, now tell me.
Sir, for example, if we take the output of A and gate is 1,
Hmm.
uh,
No, how do you know
then
that?
the,
No, how do you know that? You don't know that.
yes, sir, we can assume.
Okay, if it is assumed,
Then the output of B is a 0,
hmm.
and the output of B is the input of A. So if we multiply 0, like 0 1 is 0, but NAND of that is 1. So
Hmm.
that's I assume like 1, output of A is 1,
So you are saying
because
the
it
output is 1.
justify the condition. Yes, sir.
So your answer is I'll get 1 0, is it?
Yes, sir. Because it justify the condition. Like if we take the
No,
output of
for a
A
minute
NAND.
you assume, no, for a minute you assume that this is 1 and this is 0. Will that work? Assume that this is 1.
So we,
No, you had earlier assumed that this is 1 and this is 0. Now assume that this is 1 and this is 0.
okay, so reverse thing, huh? So
Yes, sir. Even that will satisfy the condition.
That will also work, right?
yes, sir.
Because it's a symmetric circuit. Okay.
Yes,
So
sir.
so you, if you assume 0 1 also, it is a possible state. So
Yes, sir.
you can't determine. If I tell you the inputs, I can't tell you the outputs. Correct? No?
Yes, sir.
That means it depends on what we had done with it before. Okay. Suppose I had applied 1 0. Okay. If this was a 0, then this would be a 1. And as a result, this will be 0. So the output will be 0 1. This is for sure. We know.
Yes, sir.
And similarly, if I apply the other way around, 0 here and 1 here, then you can argue that this will be a 1 and this will be a 0. Correct?
Yes, sir.
And if I give 0 0, then both will be 1. You agree with me?
Yes, sir.
Yeah. But there is at least one case where I don't know. It depends on the previous inputs. After giving 1 0, suppose I change this to a 1, then your argument is correct. This 0 will result in a 1 here, and that one will result in a 0. So it's a stable state. Similarly, after giving 0 1, if I change this to a 1, it will maintain this 1 0. Correct?
Yes, sir.
So this circuit, cannot, we cannot predict its output just by saying that the input is 1 1. In combination circuit, that is true. In a combination circuit, the moment I give you the inputs, you can predict the output. You understand?
Yes, sir.
Yes, sir.
Whereas in sequential circuits, I had to give you a sequence of inputs. Okay, the word sequential, it comes from the word sequence. So if I know the sequence of inputs, then I can predict the output. But otherwise, I may not be able to predict. In these three cases, I can predict. But in this last 1 case, I can't predict. Is that okay?
Yes, sir.
That is why we say it's a memory element. See here, it is remembering. After I put a 1 0 in the second, the second example, right? In this example, if I put a 1 0, output becomes 0 1. After that, if I change it to 1 1, it is somehow remembering this previous state. Similarly here. Is that okay?
Yes, sir.
And there is no clock here. You can see that I have not applied any clock or anything like that. So don't look for a clock. Clocks may be used in sequential circuits, I agree. But that doesn't make it a. See, for example, I can take a clock like this. So I can take a clock. So is this a sequential circuit because it has a clock?
No, sir.
It's just a combination circuit. So clocks don't necessarily make a circuit sequential or anything like that, right? And if clock is not there, it doesn't become a combinational. So it is neither a necessary nor a sufficient condition for a clock to exist. You understood, no?
Yes, sir.
Yeah. Okay. All right. Good. So what are the examples of sequential circuits that we come across? Give me an example.
Like say processor.
Right. Right. Processor is a very, you have jumped a lot. Just give me some simple ones.
Like say incrementer, like three
Right.
bit, yeah,
Right. Right.
3-bit adder or
The
something.
counter, simple things like counters, shift registers, right? They are all
Yes, sir.
examples of, yeah. Right. All right. And you must all remember the model of a combination circuit. I'm sorry, sequential circuit. So sequential circuits essentially have a, there is a combinational part, and then there are some primary inputs, and then there are some primary outputs, and then there are some memory elements here. Okay, so there may be many of these. So these inputs to this combination circuit, they represent the previous state. And this represents the next state. These are the primary inputs which we can control. These are the primary outputs which we can observe. But generally, we can't control these lines and we can't observe these lines, right? Because usually people don't bother to bring out these as outputs. And similarly, they don't give a way of controlling these lines. So that is why sequential circuits are hard to test because I can't control these lines. So if there is a circuit fault here, if I apply your D algorithm or something like that, it may ask you to make this PS equal to some value, let us say 1 1 or something like that. But I can't directly send this state to 1 1. I may not have that ability to just send it off to 1 1 like that. Correct, no? I can control these lines. If the test vector requires you to put a 1 0 or something like that here, this I can do without any problem. But I can't send this to 1 1. Similarly, If D or D bar comes here, then I can't directly observe these. Okay. So I can only observe a D or a D bar on these wires. Correct, no?
Yes, sir. Yes, sir.
That's the problem. So we have to modify the circuit so that we can actually get controllability on these wires, and we can get observability on these wires. So that is what we would have discussed. I think in the next lecture it will be possibly there. So anybody remembers how to design a decade counter or something like that? Anybody remembers what a decade counter is?
So decade counter means from high to low.
No. Decade counter means it counts the sequence 0 to 9. The word decade means 10, right?
Yes, sir.
So it will go from 0 to 9 and then go back to 0. Some people will say it's a modulo 10 counter. Okay. Or some people will say it's a decade counter. How many inputs does it have? And how many outputs will it be there? Will it have? How many outputs? It has to represent 0, 1, 2, all the way up to 9. So how many outputs do I need?
Sir, like for 3-bit, we have like 4.
So your answer is 4, right? So 0, 0, 0, 0 represents this number 0. And then 1, 0, 0, 1 represents the number 9. Right?
Yes,
So
sir.
we need at least 4 bits.
So it means we
Okay.
need a 4 like
We
storing
need
elements.
4 now. Yeah, we need 4 outputs.
Yes, sir.
So Q3, Q2, Q1, Q0. And the input is, you know, the previous state will also be 4 bits. Okay, this is the previous state. See, for example, if the previous state is 0, the next state is 1. If the previous state is 1, the next state is 2. And the previous state must be remembered in these memory elements. You agree?
Yes, sir.
Yes, sir.
And these guys will be fed back. And there are different kinds of memory elements that we can use. There are different kinds of flip flops, like your D flip flop,
T flip flop,
A flip
toggle,
flop. That's correct. And JK flip flop, right?
SR latch.
Right, right. So these are the most popular ones. Out of them, the D is the most simple one. Okay, so D means it just copies. See, the previous state is you know it just the next state is simply a copy. Right? This is a D flip flop. So this is a clock D Q. So this is called as a flip flop. Okay, and usually it responds at the positive edge of the clock. Okay, when the clock goes from 0 to 1, that is when Q is copied from D. So D gets transferred to. We also have JK or T. So here when the clock goes from 0 to 1, then Q will toggle if T is 1. If T is 0, Q will Q will remain the same. So it's a toggle flip flop. If T is 1, Q will toggle. Otherwise, it will remember and remain the same. We also have JK. Here, if J is 0, 0, then it remembers the previous state. Okay. If J is 1, 1, it toggles. Okay. Q will toggle, and Q bar will also toggle. If J is 0, K is 1, it will go to the 0 state. The output will go to 0 state. And if J is 1 and K is 0, the output will go to the 1 state. So this is like setting the flip flop. This is like resetting the flip flop. This is like remember the previous value. And this is like toggle. So these are the sort of three important ones. You can also have SR. In SR, the thing is there are you are allowed to put 0, 0, which means it will remember the previous state. 0, 1 means it will reset. 1, 0 means it will set. And 1, 1 is you are not supposed to put. Okay, so the 1, 1 combination is forbidden in an SR flip. So usually people don't particularly use this one. Okay, we don't use SR flip flops because JK is we all four combinations are permitted, and so it's better to use this one. Now tell me, how will I design a decade counter using let us say how many flip flops do we need? We need 4, right?
Yes,
We
sir.
need to remember the previous state. Okay.
And
So
we also need, I guess, 4 half adder to
that
make
we'll
a 4
figure
bit.
out. We'll figure it out. So this is what we want to do. So this is my current state, and it is given as input to a combinational logic. So this is my current state, and this is my next state, and the next state will come and get transferred. So if I am using D flip flops here, then this value will get transferred to this value. Similarly, this value will get transferred to this value. Okay. So these four values will get copied to this value. And as a result, the state will become, so in the beginning, let us say we have reset the flip-flop to 0000 state. Okay. So we can set these guys to 0000 through a reset. Then when the clock comes, this 0 is incremented to 1, and that 1 will go here. So the state will change to 1. Then that 1 will come here, the combination circuit will increment it to 2, then 2 to 3, 3 to 4. When 9 comes, it goes back to 0. Okay. Is that clear? Everybody is understanding?
Yes, sir.
Right. So let us call these as D0, D1, D2, D3. And these are Q0, Q1, Q2, Q3. Okay. So you can write down the behavior. Okay. So let us say this is Q3, Q2, Q1, Q0, and this is D3, D2, D1, D0. Okay. So if the previous state was 0000, the next state will be 0001. And if the previous state was 0010, I'm sorry, 0001, then the next state is 0010. Okay. So let us write down so these will repeat. 0101 will repeat. Here it will be 30011. Here it will be 0100. Here 0101. 6 will become 5 will become 6. 6 will become 7. 7 will become 8. And 8 will become 9. 9 will become 0 because it has to reset back. And these will not occur. So these inputs are not expected. So we can say these are don't case. Correct? Everybody
Yes.
agree? So now you have to design this D3, D2, D1, 0. Okay. How do you design that? you need Carnot maps, right?
Yes, sir.
So you will need 4 cross 4. So here we can assume that it is Q3, Q2. Okay. And here we can be Q2, Q1. Correct? So we take Q3 along this axis and Q3, Q2 along this axis and Q1, Q0 along this axis. So let us first do it for this D naught. So when Q3, Q2 is 0, 0 and Q1, Q0 is 0, 0, we have 1. The next one is 0, the next one is 1, 1 and then the next one is 0. Right? Then 1, 0, 1, 0. Then 1, 0. These are all x's. Everybody agrees?
Yes,
D1.
sir.
See D1 0, 1, 1, 0. So 0, 1, 1, 0. Then 0, 1, 1, 0. Then the last two are 0, 1, 1, 0, 0, 1, 1, 0. The last two are zeros. Then we will have two more. This is D2. So can somebody help me fill this thing? What should I write here?
So 0001.
0,
001.
0, 0, 0, 1. So this should be 0 and this should be 1. Okay.
Yes.
Right. 0, 0, 0, 1. Then 1, 1, 1, 0. Yeah, I may have made one mistake. Huh? This 8, 8, this should be here. This I have given a mistake here. These are x's and this should be 1, 0. Okay. Because this represents 8. See, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is a mistake. This should be 0, 0. And this should be x's. Okay, sorry about that. So 0, 0, 0, 1. Then 1, 1, 1, 0. So this should be 1, 1, 1, 0. Correct?
Yes, sir.
And then 0, 0. And the rest are x's. And last but not the least, we have D3. Here it is, there are several zeros 1, 2, 3, 4, 5, 6, 7, then two ones and 1, 0. So 0, 0, 0, 0, then 0, 0, 0, 1. Right? and then 1 0. So that 1 0 will be here. So now how do you minimize this? What is the way to minimize this? See, we can combine these guys, right?
Yes, sir.
Yes.
What about here? I suppose there is not too much we can do. We can combine these 4, I think. And I think we have to do it like this. Correct, no?
Yes.
Here, maybe we can combine these two guys. And we can combine these 4. And we can combine these 4. And here, we can combine these 4. I think I don't have much choice. Correct?
Yes, sir.
So give me the answers. What are the what is D naught is nothing but between these two, it's 0 is common, right? So it is Q naught bar. So you can see this Q naught becomes always inverted. D1 is Q1 Q naught bar plus Q naught bar Q1 and Q2 bar. Correct? I think it is Q1 bar. Okay. This is Q1 bar Q naught. The common between these two is Q2 bar. So Q2 bar Q1 Q naught. No, I'm sorry. This is Q1 Q naught bar.
It's only Q3 bar, right?
Huh? See, this is Q1 bar Q naught. So we are in the column Q1 bar Q naught, and the common here is Q2. So Q2 bar Q1 bar Q naught. Correct, no?
Yes, sir. Now.
Here, this box is Q1 Q naught, and the common between the top and the bottom is Q1 bar. I'm sorry, Q2 bar. Hey, I think I made a mistake here. This should be Q3, I think. No? That is what I think she was trying to tell me. It is Q3 is here. It's Q3 bar. The common one is Q3. Q3 bar. Between these two guys, the common one is Q2 bar. Q2 bar, Q1 Q naught. And the this guy is whatever is common is Q naught bar, and between these two it is Q2. And this whole thing common between these two is Q2, and common between these two is Q1 bar.
Yes, Q1 bar.
Correct?
Yes, sir.
D3 is, this one is Q1, Q0, and the common guy is Q2. And in this one, the common between these two is Q0 bar, and the common between these two is Q2 bar. Okay. So that is what it is. Okay. So now we can build the combination logic. Okay, we can write down that logic. It takes Q0, Q3, Q2, Q1, which are coming from the flip flops. Still. So there are 4 flops. So this could be Q3, this could be Q2, this could be Q1, this could be Q0, and correspondingly this will be D3, D2, D1, and D0. And we will use a clock to synchronize the all the 4 D values. Okay, so this is called as a synchronous sequential circuit, because see, when I suppose I clock the circuit, the state values here will change. Okay, and there is a, the delay from here to here may be different for different outputs, so they all get ready at different points of time. So we don't want to capture the new state unless everybody has responded. So that is why we need a clock, right? We need a clock and we need a reset. So reset is also another thing that we need to add. So when we reset the circuit, we go to 0000 state, and then when we keep clocking, it keeps going to the next state. When 9 comes, it goes back to the 0 state, and so on. Okay. So the thing is, this is the logic. The combination logic has this stuff. And when you write this using AND gates, OR gates, etc., there will be a fault model, right? They may be stuck at 1, stuck at 0, all those things will be there. So if you try to generate a test vector for one of those faults, it will expect you to activate it in a certain way. For example, it may say, I want you to go to this state, let us try. How much time do we have? Okay. So we have Q0 bar. So this is my Q0. Then we have Q1 Q0 bar. and Q3 bar then Q1 bar and Q0. So imagine that I was worried about a stuck at zero fault here or something like that. So our algorithm will say put a 1 here to activate the fault, right? So that will cause the fault to go here, and we want this to become a 1. So this should become a 0, right? So now the fault comes here. We want this to become a 0. So let us see. This 1 has already made a 0 here. So it's already done. Okay. So this is not important. So if we can send these two lines to 1 0, then that will activate and propagate the fault to the primary output. But the point is, I can't arbitrarily send Q1 to 0, Q1 to 1 and Q0 to 0 like that. Okay, and similarly, so reset can only give me all 0 state. So I can't arbitrarily allow Q3 to become 1, Q2 to become 1, and all those kind of stuff. So that is why we need some way to be able to directly set these values to known values. So that is what we will achieve using the scan design. So I think that will be covered in the next week. Is a thing clear to everybody why we need a way to
Yes, I got it.
yeah.
Yes,
All
sir,
right.
but this was there in week 5.
What did you say?
Sir, but this was there in week 5. But the
Oh, it's
question
already
was
there, huh? Oh, okay,
till
good.
week 4.
Yeah. If it is there in week 5, very good. So the thing is, we can try. See, suppose we have to go to state 9 in order to activate a particular fault. How do I go to state 9? The first I have to go to state 8. But how do I go to state 8? I have to go. So I have to go all the way back to 0 first. Okay. And then I must come back and come to 1001. Okay. So to activate the fault, it may require many clock cycles if you don't do something about it. You understood, no? If my test requires me to make the state equal to 1001, I can't directly send this flip-flop to 1001 state. It's a simple, this is an incrementer modulo 10, right? So I have to first send it to the state 8. Then to send it to state 8, we have to make it 7. And we will keep going all the way to 0. So that is a problem. And sometimes what if it comes back and says you have to send it to state 1111, right? That is not even possible here. Okay. The functionality may not allow me to take this to 1111.
Yes, sir.
So there must be some other way that we need to initialize. So what they will do is, they will we look at these 4 flip-flops as a parallel in, parallel out register. So this takes as input the Q values and produces the D values. Okay. So these are the you know the the new values D, right? And these are the old values Q. Since we don't know how to set the Q values to any arbitrary state, we can have a serial in serial out operation. We can have a shift register operation. So imagine that this is a register of 4 bits. As of now, it allows parallel in parallel out operation. But in another mode, if we can allow serial in serial out, then we can put any value we want. We can shift in whatever value we want. Even if it asks us to put it to 1111, it is possible to do so. Okay. So that requires some extra logic to take a parallel in parallel out register and convert it into a serial in serial out register or a parallel. So it needs 2 modes, one parallel mode of operation and one serial mode of operation. So we need extra logic. So you will modify the circuit, and then depending on which state we want it to be in, we can just shift that state into the state register. So that is what is called design for test. So we will redesign the circuit to be able to test it. Okay, so that is what we have covered. So you can listen to the lecture and get more value.
Yes, sir.
All right.
Yes, sir. Thank you, sir.
All right. Thank you.